Hi folks, welcome to the 4.7 video. And so this section is about the Cauchy-Euler equations. And so as a reminder of what we know, we've talked about solving homogeneous second order differential equations. Those were the sections 4.2 and 4.3. Just write those right here, 4.2 and 4.3. And in particular, those were our homogeneous ones. And we looked at the ones, the differential equations with constant coefficients as well as non-constant coefficients. And as we moved through chapter 4 this week, we took a look at non-homogeneous differential equations and focused mostly on the kind with constant coefficients. And we learned two methods, one with undetermined coefficients, and so that corresponds to 4.4. And we took a look at variation of parameters, which you can find in section 4.6. And so that's where we've been. And we are now in the very last section that we're going to cover in chapter 4. And so in the Cauchy-Euler section, we're going to be taking a look at solving non-homogeneous second order differential equations with non-constant coefficients. All right. And so we are moving away from the idea that the constants or the coefficients are constant, and rather we're going to have some sort of function of x as the coefficient. Okay. Now, I do want to say that in this section, even though this is classified as non-homogeneous, we're actually going to spend most of our time looking at homogeneous equations. All right. At the end, I'll show you one example with the non-homogeneous ones. They really put together a lot of the different methods that we've learned. And so it would be important for us to just make sure that we are really building these foundations here with the homogeneous ones, and then being able to layer in the non-homogeneous part is maybe a little bit above and beyond what we're going to do in the scope of this course. All right. And so let's begin by taking a look at where we are, right, in our concept map. So we're looking mostly at non-homogeneous. We've covered these pieces except for the annihilator method. And now we are in our final section of chapter 4 and talking about the Cauchy-Euler method. And so before we begin, I'd like to actually talk about what the Cauchy-Euler method is, or equation is. All right. Sometimes they're known just as regular Euler equations. But let's remember that we know what a linear differential equation is. Okay. And so a linear differential equation has some coefficients. So let's say a sub n x to the n, and then some corresponding power of a derivative. So dny dxn. That would be the highest power or the highest order you see in the equation. And then as we move along, we sort of have one smaller and one less derivative. And for simplicity's sake, we'll put a few dots. And then at the end, we're going to have our a sub 1 x dy dx plus a naught, no x here because it's x to the 0, y, which is going to equal some function g of x. Now, one thing that is important that characterizes this as a Cauchy-Euler equation is that the powers here, all right, so the powers that we see in terms of the degree of the polynomial actually match the powers or the degree of the derivative that we're taking. And so what I mean by that is this n, oops, that's pretty big, this n is going to be, this n will be the same as this n and this n. So if I have an x cubed here, then this would be the third derivative. But if I had an x to the 10th, then this would be the 10th derivative. And so with all of these sort of matching, that's what makes it a Cauchy-Euler equation. All right, here it's a little harder to see, but we have x to the first, and this is a first derivative, all right? And so that is what makes it a Cauchy-Euler equation. But what we're going to be focused on in this class, since we're looking at second order differential equations right now, is we will look specifically at what happens when we have some constant a x squared, and that would mean we have the second derivative plus bx times the first derivative plus some third constant times y equals 0. Okay. And again, even though this is in the non-homogeneous section, we're going to focus mostly on how to deal with it if it's a homogeneous situation. And at the end, we'll have one example where it's non-homogeneous. Okay. And so this right here is our focus. And so what we're going to do is we're going to go through a little bit of a general solution. All right. So we're going to go back to that idea of we can verify a solution by sort of assuming that we have a solution of a specific form. Okay. And so what we're going to do is we're going to say, let's assume that all of our solutions are of the form y equals x to some power. Okay, so this is our assumption. Let's say that all solutions are of the form y equals x to the m. And what that allows us to do is we can say y equals x to the m. Y prime is going to equal, well, m is a number, so we can use the power rule here, m x to the m minus 1. And then to find the second derivative, we would use the power rule again. So we have m times m minus 1, x to the m minus 2. Okay. And so what we're going to do now is we're going to take these three and we're going to plug them in to the Cauchy-Euler second order differential equation. And let's see what happens. So if we plug things in, we're going to get a y double prime. So ax squared, y double prime. So m minus 1, x to the m minus 2, plus bx times y prime. So that's m x to the m minus 1. Plus cy, and that is just x to the m. All right. And because we're starting with the homogeneous version, we want this to equal 0. And so let's do a little bit of algebra. And in particular, we might notice that if we have an x squared and an x to the m minus 2, when we multiply these two terms, we're going to add the exponents. And so we'll end up with a x to the m power, because m minus 2 plus 2 will just give us m. And we'll still have our m and the m minus 1. So all of this comes from that first clump. Plus, let's see what happens in the second one. Well, it looks like, again, we have this x and then x to the m minus 1. And if we multiply those, we'll just get x to the m. So bx to the m times m. Plus our last one, we don't have much to do. It's just cx to the m equals 0. Now, in looking at this, we've just done a little bit of algebra, but now I notice that I have a common factor between all three terms, and that is this x to the m shows up in all three terms. So I'm going to go ahead and factor that out to the front, x to the m. And let's see what we're left with. am m minus 1 plus bm plus c is going to equal 0. Okay. Now, one thing that is maybe we should have written this out in the beginning, but one thing that we might want to note is we are assuming here that x is greater than 0. Okay. Now that would be important because when we're looking at this sort of x to a power, if we had x equals 0, then we would end up with a situation where it's just 0 the whole time. And so there's nothing changing. And when things aren't changing, we don't model it with a differential equation. Okay. And so when we look at what must be true, it must be that, so this chunk, x to the m, will not equal 0. And so this thing in the brackets produces these solutions for this differential equation. Okay. So this am m minus 1 plus bm plus c, whatever are the solutions for that, that will help us find the solutions for our differential equation. Okay. So let's go ahead and try a bunch of examples. And what we're going to see is that we're going to have 3 cases that should look very familiar. All right, we're going to look at real and distinct roots. You can already see that at the bottom of the screen. We're going to look at real and repeated roots, and then we're going to look at complex roots. All right, so we'll work through a few examples of each one, and at the end, we'll finish with a non-homogeneous equation. Okay. So it turns out that if you have a Cauchy-Euler equation and you have 2 distinct roots, they're real, they are distinct, your solution will be of this form. Okay. Now it looks kind of similar to what we had in the earlier section. And so it might be worth going back to sort of take a look at that and see how these two compare. Okay. I think that sometimes when we are learning things at different moments in time, it doesn't really stick with us how they are similar or how they are different. But since we are right in the middle of this right now, I would compare these to the ones from 4.3, the general solutions from 4.3. Okay. And that's partially why I asked us to take a look in our discussion last week, like, what are the 3 cases and how are you going to memorize them? Because I knew this week we were going to add more kinds of cases. And so it's really important that we're able to keep track of them. Okay. All right, so let's take a look at this equation. Example 1, solve the initial value problem. All right, so we're going to start off with an initial value problem. All of the other ones will just be regular ones, but I want to make sure we get an initial value problem in here. So we have 2x squared y double prime plus 2xy prime minus 15y equals 0. And I have initial conditions that I'm going to sort of save and use at the end. Okay. And so our first thing here is to notice that we have, since this is a Cauchy-Euler equation, all right, we want to find roots. All right, so since this is a Cauchy-Euler equation, we're going to go ahead and find the roots. Now, I know that we're in the Cauchy-Euler equation section. You know that we're in the Cauchy-Euler equation section, but it would be important to notice that we have sort of the squared here and then the double prime. We have a power of 1 and a single prime. And those are the indicating factors that we have a Cauchy-Euler equation. Okay. And so finding the roots, all we're going to do is we're going to use the A, B, and C from our equation. We're going to plug them into this equation, the one that produces the solutions for the differential equation. And we're going to find values for M. Okay. So let's go ahead and copy that down. We have in our equation, A equals 2, B equals 2, C equals negative 15. And so when I plug those in, I'm going to get 2m minus 1 plus bm, or 3m, and then plus c, or the negative 15. And that's going to equal 0. All right. We do a little bit of algebra. We get 2m squared minus 2m plus 3m. So that's going to give us plus m minus 15 equals 0. We're going to go ahead and say, I'm so glad I learned how to factor so well a long time ago or recently. But we should get, let's see, 2m times m. I think a 5 and a 3 should work here. Negative 5 and positive 3 in particular will give us the plus m in the middle. And I know this is so silly, but we want to just be really careful that we solve correctly here. Our m is not 2/5, but it's 5/2. And then it's also negative 3. So negative 3 and 5/2. All right. So since this is the Cauchy-Euler equation, we found the roots. And what we're going to do is we're going to plug them into the general form of the equation. Okay. So let's go ahead and sub into general form of the solution. And so if we look, we're going to write y equals c1 x to the m1 plus c2 x to the m2. So we're going to get y equals c1 x to the negative 3 plus c2 x to the 5/2. Right? Now it's slightly different from what we saw in section 4.3. So we really want to be careful that we are remembering to apply the correct thing. Okay. Now we are going to go ahead and apply our initial conditions. All right. And so I notice that y1 equals 0, or y of 1 equals 0, and y prime of 1 equals 1. So let's go ahead and sub those values in. We're going to get c1 x to the negative, c1 1 to the negative 3 plus c2 1 to the 5/2 is going to equal 0. That's the first initial condition. And let's go ahead and simplify that a little bit. We'll get c1 plus c2 equals 0. All right, so that's our first equation. But in order to use the second initial conditions, we have to take a derivative. And since we are having an equation like this, we're going to use the power rule. Okay, so y prime equals, let's see, negative 3 c1 x to the negative 3 minus 1 is negative 4 plus 5/2 c2 x to the 5/2 minus 1 is 3/2. And then let's go ahead and plug in our initial conditions. So we have negative 3 c1 times 1 to the negative 4 plus 5/2 c2 1 to the 3/2, and that, my friends, is going to equal 1. And so when we clean this up a little bit, we'll get negative 3 c1 plus 5/2 c2 equals 1. All right. Now, you could take the two equations, c1 plus c2 equals 0, and this one, and you could go ahead and put them into a matrix. That would be okay. If you wanted to solve, I like the elimination method for this one. So I'm going to take the first equation and I'm going to multiply by a 3. Okay, so using elimination, I've got 3c1 plus 3c2 equals 0. And when I stack that on top of the other equation, negative 3c1 plus 5 halves c2 equals 1, I can see that I'm going to get 1 on this side, and I will end up with 11 halves c2 on the left-hand side. And so this gives me a c2 value of 2/11. And since C1 plus C2 equals 0, I know this means that C1 equals negative 2/11. Okay. Now, if you put a box around this and you call it a day, you didn't really finish the question, right? We want to go ahead and put this back into our final answer. And so we want to have our final answer, which is going to be this equation that we got up here, and you're going to plug in the C1, C2 values that you found. All right, so our final answer here is going to be y equals negative 2/11 x to the negative 3 plus 2/11 x to the 5 halves. All right. And so there it is for you on one screen. All right, our first initial value problem looking at a Cauchy-Euler equation. Now, for the rest of them, we're primarily just going to be doing steps 1 and 2, okay? I just wanted to make sure we practiced one with the initial conditions so that we would know how to find them, and emphasize, because I still have a few friends in this class who don't want to write that final answer for me, and I can't give you that full credit if you don't write that full answer. So make sure you write that full answer, okay? All right, let's take a look at another equation. I do a quick check. I notice that I have x squared and a y double prime. Those are the same power. X to the first and a y prime, those are to the same power. So I look at this and I say, hey, I know this is a Cauchy-Euler equation. So the first thing I'm going to do, I'm going to go ahead and find my roots. And so when I look for the roots, I want to identify A, B, and C. And we're going to plug them into A, M minus 1 plus BM plus C is equal to 0, okay? And that's what we're going to be putting our A, B, and C into. And so we have M times M minus 1 minus 2M minus 4 equals 0. Let's go ahead and do a little bit of algebra. M squared, let's see, minus M minus 2M is minus 3M minus 4. Ooh, this is a nice factoring one, right? M minus 4, M plus 1 equals 0. And so we end up with two roots, M equals negative 1 and positive 4. And so we can see here that these are different roots, and they're both real roots. So we can find the general solution, general form. And that is y equals c1 x to the m1 plus c2 x to the m2. And I'm going to go ahead and, in no particular order, I'm going to put the negative 1 first and then the positive 1, but you're able to switch the order and it doesn't matter. Okay, and by negative, I mean like the negative root and the positive root. So one is negative 1, the other one is positive 4. Okay, and so there is that second question for you. All right, so let's move on to the second case. What happens if we have real roots that happen to be repeated? And it turns out that in a similar fashion to the real repeated roots in 4.3, it looks very similar, except there's something extra there. And in this case, the something extra is the natural log of x, okay? So let's go ahead and take a look at this equation. It is Cauchy-Euler because I have a second power and a double prime, a first power and a first prime. The first thing I'm going to do, I'm going to find some roots. While I'm here, I'm going to say A equals 4, B equals 8, C equals 1. And we're going to plug them in. So it'll be A, M minus 1, plus B, M, plus C equals 0. And if we go ahead and do a little bit of algebra, we get 4m squared. Let's see, minus 4 plus 8 is plus 4m plus 1 equals 0. And this is actually a perfect square. 2m plus 1, when I square it, will give me the 4m squared plus 4m plus 1. And so if I solve this, I'll end up with m equals negative 1/2. Okay. And there's only one root because it's repeated, right? It's a negative 1/2 and then another negative 1/2. And so we want to make sure that we use the correct form for our general solution. And that is going to be this one right up here, right? So y equals c1 x to the negative 1/2 plus c2 x to the negative 1/2 natural log of x. And this, you can go ahead and put a box around. We don't have to find values of C1 and C2 because they didn't give us initial conditions, okay? All right, let's do another one like this. Maybe we'll keep them both on the same page so we can see. I see a squared and a double prime. I see a first power and a single prime. And so I know that I want to go ahead and find my roots. And you don't have to do this. I like to list out my A, B, and C so I don't make any sign mistakes. All right. And then we're going to plug them in. So A, in this case, 1, M times M minus 1, plus B, M, so minus 7M plus 16 equals 0. Let's go ahead and algebra. We've got M squared minus 8M plus 16. Ooh, that's a perfect square. M minus 4 squared equals 0. So M will equal 4. And this is as above a repeated root. And so we want to make sure we use that proper form of the general solution. And so we're going to get y equals c1 x to the 4th plus c2 x to the 4th. Don't forget about that natural log of x. All right. And so let's get both of these on one page for you. There's your 2 examples on real and repeated roots. All right. Let's take a look at what happens when we end up with complex roots for the Cauchy-Euler equation, okay? So complex roots, they do have a longer equation, and it is important to think about matching all the different pieces properly, okay? And so let's go ahead and write this out, all right? So quick check, it is Cauchy-Euler for the same reasons that we've said before. And so that means that our first task is going to be to find the roots. In this case, we have A equals 1, B equals 3, C equals 4, right? And so when we plug those in, we get 1 times M minus 1, plus 3M plus 4 equals 0. And if we go ahead and simplify, we have m squared plus 2m plus 4 equals 0. I can see from here already that it's not going to factor. So let's try the quadratic formula. Negative b plus or minus the square root of b squared minus 4 times a times c will give me negative 16 over 2. And this gives me negative 2 plus or minus root negative 12 over 2, which gives me negative 2 plus or minus 2 root 3 I. And sometimes I leave sort of an aggressive space between my root and the I. You can also put the I in front of the square root, and that would be fine. And once we have this, we notice that a lot of things reduce. And so we end up with negative 1 plus or minus I root 3. Okay. Now you'll notice that in the general form of the equation, I have an alpha and a beta. This is very much like the mu and the lambda that we used there. So a lot of times in the complex one, we'll have some sort of Greek letter to signify the real part of the number. Whoops, that's not what I meant to do. The real part. So in this case, negative 1, and then the imaginary part, or the root 3. Okay. And so this negative 1, this is what we call alpha in our equation, and this root 3 would be our beta. So alpha and beta. If you don't want to change the letters, you want to stick with the lambda and the mu. All right. Alpha is like the lambda that we saw in 4.3, and beta is like the mu that we saw in 4.3. All right. Differential equations uses a lot of Greek letters, and so it's really up to the user's choice what they use, but the more important thing is that you put them all in the right place, okay? And so we have our alpha as negative 1 and our beta as root 3. So if we plug those in to our general equation, all right, we're going to go ahead and say y equals x to the negative 1, that's my alpha, c1 cosine of root 3 natural log x plus c2 sine of root 3 natural log x, right? So we can go ahead and put a box around that. We do not need to find C1 and C2 because we were not given any initial condition, all right? However, it does seem like we're going to need to find our C1 and our C2 in example number 2, okay? So let's take a look. We have here an Cauchy-Euler equation. There are the classic signs, all right? That's squared and the double prime. And if we go ahead and set this up, that means first thing we're going to do, we are going to find roots. Okay, so we're going to go ahead and find roots. And we're going to do that by saying my A is 4. My B is, ooh, let's be careful. B here is 0. And our C is 17. Right? So we get 4m, m minus 1, plus 0m plus 17 equals 0. We do a little bit of algebra. 4m squared minus 4m plus 17 equals 0. We say that's not factorable, so let's use our quadratic equation. And this 16 minus 4 times 17 all over 8, right? 2 times 4. And we go ahead and we simplify a little bit. I believe this whole big clump here becomes, and when I take the square root, will become 16i over 8. And we can go ahead and reduce here, and we should, okay? So 1/2 plus or minus 2i. This allows us to see that our 1/2 is our alpha, or we might want to call that our lambda, and the 2 is our beta, or our mu, if you want to use the same letters as before. Okay. So we're going to go ahead and plug those all in to the equation. And what are we going to get? We're going to get y equals x to the 1/2. And we're going to have C1 cosine of 2 natural log x plus C2 sine of 2 natural log x. And that would be our general solution, right? But since we're given initial values, we can go ahead and find values for C sub 1 and C sub 2. So let's go ahead and find some initial conditions. And what happens when we apply those initial conditions. And we're going to start off with the first one. So y of 1 equals negative 1, 1 to the 1/2, C sub 1 cosine of 2, let's see, natural log of 1 plus C2 sine of 2 natural log of 1. And the good news here is natural log of 1 is 0. All right, and so we have sine and cosine of some very nice unit circle values. And so we get negative 1 equals, let's see, this also goes to 1. We end up with C1, cosine of 0 is 1, sine of 0 is 0. So the C2 part goes away. And this is what happens with a lot of the more complicated equations, is that the boundary or the initial values actually are quite nice. Even if the actual equation is gross, the initial conditions will usually be nice, and then things will sort of cancel out. Okay, so I bet when you apply the second initial condition, the C1 is going to cancel out, and then we'll just be able to have C2. We don't even need a system of equations. Okay, so let's see. Our second one was y prime of 1 equals negative 1/2. And so before we get there, maybe we should take that first derivative. All right. I'm going to go ahead and use product rule here. All right. So my first x to the 1/2, that'll be 1 over 2 root x times that whole clump plus square root of x times the derivative of the inside. So let's see, negative 2 over x C1 sine of 2 natural log x, because I've got to use chain rule there, plus 2 over x C2 cosine of 2 natural log x. All right, so that was probably the worst part of the whole problem, is that product rule there. But now we're going to plug in 1 for the x values and 1/2, negative 1/2 for the y value. 1/2 equals 1/2. Let's see, we're plugging in 1 for x. So C1 cosine of 0 plus C2 sine of 0 plus square root of 1 is 1. So negative 2 C1 sine of 0 plus 2 C2 cosine of 0. All right. Let's see what goes to 0, what goes to 1. So this is going to go to 0. This is going to go to 0. This goes to 1. This goes to 1. And so we're left with negative 1/2 equals 1/2 C1 plus 2C2. So I was almost right. We don't have a system. We can actually plug in our C1 here to find C2. And so we'll get negative 1/2 equals negative 1/2 plus 2C2. And we'll get 0 equals 2C2. And so our second constant actually is 0. And this is going to give us, because now we got to go back, we're going to fill in our C1 and our C2 in that general form. And so let me go ahead and squeeze that right down here. We're going to get y equals x to the 1/2. We're only going to need the C1 term because C2 went to 0. So negative 1 cosine of 2 natural log x, which equals, let's just bump that negative sign to the front, negative x to the 1/2 cosine of 2 natural log x. All right. So a nice beefy one with some good algebra in there for the last example. All right, so for this non-homogeneous case, I'm going to leave this here as sort of a challenge level question. Okay, and so I'm going to give us a skeleton of how we can solve this. And if you send me your work for this question, we'll assign 5 extra credit points for this. Okay, now I won't leave you totally high and dry, though. I'll give you sort of an outline of what should be done in order to solve this question. And this is just sort of one suggestion on methods that you might use. But one thing that we've learned with the homogeneous versus non-homogeneous is that we usually solve the left-hand side first, and we pretend almost like it's homogeneous. And then we go back and we solve the other side, okay? And so the first thing that I would encourage you to do is find roots of the left-hand side and write a general solution. Okay, now this will be our y sub c part, y sub c. Okay, so if you haven't watched the previous videos yet, take a look at those to see what y sub c stands for. But that would be my first suggestion to start there. After that, I would find the Wronskian from y sub c. Okay, find the Wronskian for y sub c. After doing that, I would turn the differential equation into linear form. All right, to find y sub p. there is a formula in your textbook and from notes that you can use to find this y sub p. All right. Now, this is a fairly lengthy problem, all right? So you're going to find the roots of the left-hand side to find that y sub c. You're also going to find the Wronskian from the y sub c. This Wronskian will be useful in finding your particular solution, your y sub p. And as I said, there's a formula that you can use to go ahead and do that. You'll also need some other integration techniques. So something along the lines of more than just a u sub, more than just a just a regular chain rule or something like that. Okay, so something beyond that could be partial fractions, could be integration by parts, but you will need some of those techniques to solve this particular problem. Okay, and at the end, you want to make sure that your final answer is your y sub c plus your y sub p. Okay, and so if you go ahead and send that to me, it will be worth up to 5 extra credit points, and this is due by Saturday. And that will be Saturday. Let's see, what is the date? July 17th, 11:59 p.m. And you can just email your solutions to me. Okay. All right, so folks, that is it for 4.7. Thanks for watching, and let me know if you have any questions.